Assalamu alaikum students. Today is experiment number 8, ODL lab number 9 actually. And as you can see the circuit diagram over here. Let me just share the screen also actually. Okay. So I hope my screen is shared and I hope everyone is seeing my screen. This is also being recorded, so hopefully my voice is being recorded and all that stuff. So this assistant, let me check. Yes, voice is there. Okay, so this is experiment number 8. That is a 5-volt relay. That is the model number written over there, HK4100F-5 volt. Dash 5 because this relay is available in many different voltages. I will just go through the data sheet and we will see all that. So it's going to be a 5 relay module with 8 node. 8 node means that 8 appliances can be controlled over here. Those appliances can be any object. It can be a fan, it can be a bulb or something, whatever. It can be done. And the only limitation on this one is this, that we will see the data sheet just now, and you will see that the data sheet has a limitation that the current rating of the device should not be more than 3 amperes. So this is that relay. I have selected this smallest relay that is available at Hall Road, and this relay is approximately, I guess, 40 or 50 rupees per piece. Anyway, when we will come on to that manufacturing part, I will tell you what you have to do and what you don't have to do. So this is actually the experiment circuit diagram, and as I have told you previously on, and those who are coming on late in this class now, this experiment is actually a little different from what you have been doing up till now. Up till now, from experiment number 1 up till experiment number 7, you have been using something or doing something visible, in which there was some LED, there was a dot matrix, there was a 7 segment, or there was a RGB dot matrix or something, so in which you can actually control it by through some dip switches. Now, since the world has actually moved on to automation means that you can actually control any device remotely or maybe at any given point from somewhere, or maybe from your smartphone or from your website or something. And if you want to actually do that, or you want to have that ability for your device, then you have to actually make an IoT module. IoT means Internet of Things module, and certainly that device has to be miniature because this has to go inside the power socket at your homes. Now, as you can see in this circuit diagram, as I have told you, they are relays. What are relays? We'll just talk on that just a little later. And then there is a power module over there, which is the power module which is going to take some AC voltage in. And what I mean by that, if you can just zoom in over there, this is the AC voltage, 220 volt AC coming in over there and passing through some resistor and C1. We will talk about that later on. And then it's just a black box. What is inside it, I'm not concerned on that, but just for some enthusiasts who are interested in this one, it's actually a isolated DC AC to DC converter over there, which may be having some rectifier and then some DC to DC converter inside it, which is actually housed inside a black box. And that black box is something over here that is produced by the Highland company. It has an input of 100 to 240 volt AC, and it's a 50 to 60 hertz device, and output of 5 volt DC slash 5 watt, which means that it can output 1 ampere of current, which is almost reasonable for our case over there. And just at the output, you can see there is a capacitor. In fact, there are now 2 capacitors. I will tell you that why these 2 capacitors are now needed over there. One is a 100 microfarad SMD silver, which is something like this shape, and another one is a SMD 1206 size 100 nanofarad. Now, you have been using 1206 100 nanofarad very easily. It has been available up till now. This one is a new addition. Why? Because normally 1206 and 1210, you will not find a 100 microfarad capacitor in that size, because 100 microfarad is a larger size. So this is an electrolytic capacitor, which is 100 microfarad SMD electrolytic. We normally the word used is silver over there, because you can see the shape is actually cylindrical, but again it's an SMD component. It's not a through hole component, And when I will talk about the PCB design, I will tell you that this PCB footprint, you have to find it out yourself. And then the resistor is already there. That is actually going to be a 330 ohm resistance, SMD again over there. And then an SMD LED of any color. You want to use red, green, blue, that's totally up to you. The size is just 1206 SMD over there. And the whole PCB, if you can, the design over here, it's only having one LED over there, which means we have tried to actually make it power conservative also. Why? Because this whole experiment, let me just tell you a little bit on this one. In my lab at my home, I have many of such like modules which are placed inside the power sockets over there, and I can remotely access them, and I can turn on and turn off any of my device. Supposingly I am sitting in my lab at present, and I can control any of my lights in my lab. And I guess I have showed you previously also some of the pages which I have over here. This is one of the pages over there. So these are some controls over there in which I can actually turn on, turn off, or fans over there. So this is one of the websites over there, and those power sockets, they have a similar kind of. Now how many relays I am going to use, that will decide, okay, how many devices I want to control. So maybe if in any room there are like 5 or 6 devices over there, and those devices you want to control remotely. Remotely means, does not mean by a remote, it can be from any website. Or maybe you are traveling to your home and you want to turn on your device. So maybe you need some app, and that app is actually going to connect with your some Wi-Fi router at your home, and then it's going to give signal to your socket, and then that socket is actually going to turn on that relay, and then relay is actually going to turn on that device which you want to control. Maybe you want to turn on your AC, your fan, or your light, or maybe you want to just turn it off so that there is no power wastage. So this device which we are designing, it has to be size conservative. This is very, very important. And I'm not giving any size dimensions over there, but the ideal size of such device would be that you can actually make it in the size of less than 6 cross 3 inches. 6 cross. What I mean by this over there, I don't know how many of you have an idea on this one. Normally the sockets available at your home on the wall where you have the piano switches, when you turn them on, the size of those boxes are 6 by 3 or 3 by 3. Now 6 by 3 boxes, your circuit should be less than that size. When I'm saying 6 by 3, it should be something like 5 by 2, maybe something like 4.5 by 2 or 2.5 or something. This should not be 6 by 3 exactly, but I'm not giving any size over there. Let's see how you can design this one, and I have given some instructions in this experiment which will help you over here. So in this overall, the first thing first is this, that you are actually going to have a power module, and that power module is HLK5M05 over there. So this module is actually a device which is actually going to take AC voltage, because on your power sockets you have AC circuit, AC voltage coming in. Now that AC voltage is going to be taken up inside this device, and I don't think so you are not aware of this one. Then the AC, whenever you are talking in terms of some electrician or something, they use the word in Urdu they call it the garam tar and a thandi tar. So that is shown by that red color wire, which is actually the live wire, and the thandi tar, which we call it as the neutral, we call it as the AC ground, which I have shown over here in blue color. So you can see over there that the device is taking that live and neutral wires inside it, and something circuitry inside that, which is actually going to be certainly a full bridge rectifier, and then there is going to be some DC to DC converter inside it, and then it's going to give you that 5 volt. Now let me remind you, this device Highlink is a little expensive for very maybe like the last time I bought this price from China, this was approximately 700 to 800 rupees. So maybe it has now increased a little bit more. So I'm not going to ask you to buy this one, but I'm asking you to use this one in your design. And we are going to have to make the footprint also, because this device is totally a third party. So it's not going to be available in LTM. So we have to design that one. For that purpose, we will need a data sheet. I have given you the 2 data sheet links. One is for the power module, the other one is for the relay. And the relay which we are using over here, as I have told you previously, it's actually an HK4100F DC 5 volts. dash SHG, whatever. So you can see over there, it's written over there on this uh, relay also, that this is a 3 ampere 250 volt AC, which means that if you are actually having an AC voltage device turned on, turned off, it can have a maximum current rating of 3 ampere. And all those fans working at your home, I guess they are not enough, even 1 ampere. So all the fans, LED lights, lamps, or even your laptops, they can actually be run on this one very easy. So technically speaking, any device which is less than approximately 700 watts of power can easily be turned on and off over there. In fact, this relay, I'm using these relays a lot. In fact, all my house has approximately 40 or 50 of these relays. So technically this relay is a very good one, but don't worry on this one. This relay can also be found as second cheapest also at Hall Road. So be very careful when you're buying this. Don't buy some counterfeit, copied Chinese item. Okay, so this is a relay. As you can see, this relay is a 6-pin device, and I have given you the top view of this here and here in the structure, 3D structure, and here I have given you the pin configuration also. I have taken this pin configuration from the the data sheet, and I have also taken this from the LTM model, which I already have made it myself, but you have to make it yourself. Now if you see this device, a relay. Now what is the relay? Let me go on towards the relay part. A relay is a device which is actually an actuating device. As I told you previously also, a relay is an actuating device. You can go through this text yourself over there, plus the link which I have given you on the website. This is the second link over there. It's a very good link which will give you an idea on, this is a YouTube link over there, and it tells you a lot about how a relay can be actually working. Over there you can go through this link yourself. So a relay is actually a device by which you can actually have an actuating device which will actually control any device turn on and turn off. Now you all know a transistor is actually a turn on and turn off device, but by transistor you cannot turn and turn off a AC device, because an AC is an alternating current where the voltage is actually going on in the positive direction and then going on in the negative direction. So a transistor cannot work in that, because transistor always have a current going on. If it's an NPN transistor, you always have a current going from the collector to the emitter. You cannot make that current flow from the emitter towards the collector over there. So technically you need a relay. What relay is actually an electromagnet. So you all know what is an electromagnet. A simple material, an iron core or maybe some ferrite material, and on that ferrite core you have some winding done on it, this one. So you can see in the small animations over there what is being happen. This is a relay coil, this one where my mouse is hovering. This is a relay coil over there, and as soon as I give a DC current to this one, so what happens, this fulcrum, the red color fulcrum, gets attracted. Okay, why? Because you all know whenever there is going to be a solenoid or maybe an electromagnet, it's going to have some force of attraction. It's going to actually act as a magnet. So that magnet is actually going to attract that lever over there, and that lever is actually going to have that device turned on. So what happens over there, any device at your home requires two wires. One is the live wire, other one is the ground wire. Now supposingly on this side where my mouse or cursor is at present, I have the live wire connected over here. So what means, when the device is turned off and then I turn on my DC over here, and certainly this is going to be done by a transistor. So this relay is going to be turned on. So what will happen, the fulcrum will actually move on towards this position, and then the device is actually going to be connected at this point where my mouse is, and what will happen, the device is going to be fed the live wire. So this means that the same thing which you are doing actually by a mechanical switch, a piano switch at your homes, this is being done by a DC signal which is being given to your relay coil. So relay has an electromagnetic coil, and that coil has the capability of attracting a fulcrum towards one contact point. Now based on this one, if you are seeing this diagram very easily over here and you can understand this thing, that this is the common point, which means that you are actually going to have this relay working as always connected with the live wire. but this is going to be connected with your device, meaning that this point where my mouse or cursor is at present, this point is called as normally open. Okay, this point where my mouse or cursor is at present is called as normally open. Normally here means that when the device is non-energized, which means it is not given any DC 5 volts or whatever that voltage of the coil over there. So when this is going to be given a 5 volt signal, then it will. So previously this contact point is open when this is not energized. So this is called as a normally open contact point. Now there can be a device, similarly you can see over here what is happening over here. You can see a relay coil, and as soon as you will turn on this switch can be a transistor switch. Remember, this is a transistor switch. So what will happen? You will have the device working over there, just like this one. So as soon as you will have that energized coil, and now you can start any motor, any fan, or whatever. You can have anything. So from a DC circuit, you can control an AC circuit by using a relay. So relay, you can go through all this stuff very carefully. This is a very important part of it, and relays are very good. The YouTube video, please go through that one yourself. You will understand a lot from that relay concept. Now going on to the relay which we are having or which we are using in our experiment today is actually HK4100F/410. It is actually two models over there, but I am concerned with the first model over here, which is HK4100F over there. I guess this is 3 ampere switching capability. I just told you on that one over here. The contact form is either 1C, 1A, 1B. Don't go into that detail because this is the first relay you are going through. So this is going to be contact material is silver alloy, certainly, because this is going to be working for like many years to come. But certainly the contact ratings has been given, just like I told you previously, that it has 3 ampere 250 volt VAC or 3 ampere 30 volt DC. Any one of you who can answer me on this, why the DC voltage range is small and the AC voltage range is large? Do answer me after this lecture. If anyone has the answer, I will give that answer in the WhatsApp group. The maximum switching voltage, you can see this is written as 300 volt AC or 60 volt DC. This is the maximum value, which means that the device can still work up till that point. The maximum switching current, which means a 3 ampere device is the maximum device you can actually attach. The maximum switching power is 750 VA or 90 watts over here. And the contact resistance is 100 mega ohm. Now this is the contact resistance when they are open. Now you may say when it is open, it's actually a insulator. It will having no resistance. But remember, there is no concept of insulator in electrical engineering. Any two contacts which are even separated by maybe like 1 meter, and if there is some air involved inside it, you can have like maybe like 200 or 300 kilovolts of voltage applied, and that air gap is going to conduct electricity. Why? Because there is a resistance involved. When that resistance gap is complete, your device starts to work over there and it starts to conduct. So this contact resistance is 100 mega ohms over there, which is actually a very, very high value. So it can be work easily at approximately at your voltages at your home. Electrical life, which is written over there, it's very important one, which is the electrical life, which means that the device DC coil, it can have 1 into 10 raised to power 5 operations. OPS means operations over there, and with a limitation that there are only 30 operations per minute. अब इसका मतलब ये नहीं है कि आपने एक रिले राइज कर दिया है और आपने किसी बच्चे को हाथ में पकड़ा दिया अपना स्मार्टफोन और वो ऑन ऑफ ऑन ऑफ ऑन ऑफ ऑन ऑफ करता रहे और वो 30 ऑपरेशंस पर मिनट से भी ज़्यादा करता रहे, तो ऑफ कोर्स द डिवाइस विल एक्चुअली बी फॉल्टी. अवल तो आपका बल्ब या फैन है वो भी खराब होगा, प्लस रिले इज ऑल्सो गोइंग टू बी getting faulty. And then as far as the mechanical plunger or that fulcrum is concerned, it has 1 into 10 raised to power 7 operations, which is huge, making a time span maybe like even if you are turning on and turn off maybe a device for like maybe like 50 times a day. So you can see that how many days your relay can actually work if it is original. Again, I'm using the word original because I have encountered this relay a lot at Hall Road and second quality or third quality also. So this is a very important factor whenever you are buying relays. In fact, in Pakistan, relays are never found as the best quality. They always are second quality or third quality over there. So be very careful whenever buying relays. Then there is some general data, and I hope you can go through this data yourself. It's very simple. It's about the humidity, weight, shock resistance, and whatever. Now the data which is applicable to us in as engineers, this is actually the data which is the nominal voltage VDC. As I told you that this relay comes in different voltages. It can come at 3 volt, 5 volt, 6 volt, 9 volt, 12 volt, 24 volts. So this means that this device can actually be available at 6 different types of voltages. Our relay which we are using is at 5 volt, and the coil resistance at 20 degrees centigrade with a plus minus 10% over there. The resistance is now this relay is actually coming in 3 different varieties. I don't know the one which you are using at present, or the one which you will be soldering is going to be which one of them. I will confirm on that later on. So this is the resistance of in ohms. So when you are going to have a 5 volt apply on that coil, because that coil is actually copper, okay, that copper is going to have some resistance. So when you are going to have a 0.15 watt resistance, this means that 0.15 watt coil, so this means the resistance is small, and when you resistance is large as compared to this value, because when you increase it to 0.36 watt, the resistance is small. And I guess this is completely true, because when resistance is small, current is going to be large, and then I square R losses are going to be large over there, and which is actually shown by 0.36 watt. Maximum operating voltage for our case is 3.75. Maximum operating voltage means that if somehow your power module, which we are using in our case, it drops down to something from 5 volt to 3.75, or maybe like 4 volts or something, any near value, it will still work. It will not have any problems. And the minimum release voltage is 0.50, which means that you require at least 0.50 voltage so that the fulcrum can be released. Okay, this is very important data, because when you are going to control this device, you have to actually have this data from any microcontroller or anything. Now maximum applicable voltage is 6.50, and we are not going to go towards that. Our value is 5 volt, and we are going to go near that very carefully and easily. Now coming on to the next data, this is again a general information. This is HK4100F, which is actually DC 5 volt, because I have 5 volts over there. And then there is some data over here which you can see over there. I have a plastic seal type or a floor solder type over there, but our case, I guess this is an plastic seal type. As you can see, it's a plastic. And then the coil power is 0.36 watts over there. Anything? So I guess there is some student trying to enter. I guess Sir Bilal is there. No, beta, you have to make the PCB also. You have to first of all make the library, and then you have to make the PCB also. Actually, going back to this one, I guess Bilal is saying. Bilal, if there is anything coming up or any issue, please text me on WhatsApp. I have that on, so I can have any communication. Meanwhile, the screen is being shared also and then recorded also. Okay, so the coil power, if it is nil, then it is 0.36 watts. If it is D written, then it is 0.15 watt. And if this is H, 0.2 watt. Actually, I have one relay in front of me at present on my table. I can just confirm on this one what I have been getting. I guess this is H in front of me. This is an H over there. So certainly this means I have 0.2 watts relay available at Hall Road. This is the one I have in my hand at present, and this is the same shape or same color, yellow color, which I have shown you. The contact form is either 1C, 1A, and then this is one coil and 1A, and then if it is nil, then this is just 1C. Mounting termination, this means that it's always going to be connected to a PCB, and this is going to be a through-hole device. Special request codes are there whenever you are going to have a device made without any leads or without lead free or something like that. So I'm not going to go in that detail. Now the most important thing by which you are actually going to design your footprint is actually this area of your data sheet over here. As I've shown you, this is those two common points, which means that the common point, just like this one I have shown you just now, this was the common point over there. So when this common point is there, this common point on our data sheet is actually this pin, these two pins over there. And then it is also connected. If I see the circuit diagram, you can see this is connected over here, these two pins, and then this pin. Now if you see this one over there, this is the top view. So when you are seeing this one, so these two pins where my mouse is hovering at present, these are the two common pins. And then which pin, here or here? Now this pin, it will be this one over there, because I'm seeing from upside down. Again, this is the top view over there, and this is the common pin over here, and this is the normally closed pin. Now I told you just now that there is a normally open and normally closed. So this means that the fulcrum is, when the DC coil is not energized, this is going to be connected with NC, which is normally closed. And when you are going to energize this coil, CO, I have named the one end of the coil as coil dash A, the other end of the coil as coil dash B. This does not mean that there are two coils. This is actually just the end of the two coils, because this is going to be energized by DC over there. So this is going to be energized over there, and when you are going to energize this contact which is normally closed, this common point will be connected to normally open. This is very important over there. So when you are actually want to control a device, you have connected 5-volt signal with the coils. So the device you want to actually turn on, if it was initially off and you want to turn it on by energizing the coil, you are going to connect it at the normally open pin. This is very important, though that you can actually have the control over. So if I go back to the data sheet again over there, now how you are actually going to make the model of this. This is actually the most important thing over there, and I will do that in front of you. Now if you see over there, this is the PCB layout over there, and I guess this is easily telling you that if these are the pins over there, and on these pins you are going to have the outer marking, and then you are going to have placed this pads, there are 6 pads over there. So the distance between the two pads, again this is in mm over there, so 10.16 over there, and then this distance is 2.54, and then this distance is 7.62. As far as the outer marking is concerned, you will go back on this diagram. You can see I'm not concerned with the thickness of that, whatever is happening over there. I'm concerned with the outer dimensions, which are 10.5, and this dimension over there, this is 10.5, and I guess this dimension, if it is written over there, yes, this is 15.5. So this is 10.5, and then there is 15.5 over there. So these are the 6 pins, 1 2 3 4 5 6 pins over there, and this pin is not circular in nature. This is the 0.71, but again we will have only a circular hole over there, because normally in Pakistan the PCB manufacturers, they don't have the ability to make square holes or rectangular holes, as you can see over there. It's not square, it's not circular hole, it's a square hole or a rectangular hole, as you can see over there. Now, so the first thing first, if I go on my LTM, I have opened a new over here, a new PCB file over here. And when I want to actually have this new PCB file, let me just increase this, sorry, on this one. So, okay. So I hope I can actually see this one. Now, first thing first, whenever you are going to do such minute works in please have this habit, change it to metric, and change this grid. I have told you previously in the very first lecture, I told you, make it to step X and step Y, the least smallest you can actually have it. Why? Because so that you can actually have very small minute details over there. So I'm just going to make this 0.025 and this okay. Now I'm going to design my relay model over here in LTM, and then I'm going to import it into the PCB library. Now I'm not doing this directly in the PCB library, because I won't find that much control of moving my mouse by 0.025 millimeters in the X and the Y direction. Okay, so first thing first, if I go back on my data sheet, I want to first of all make a square of 10.5, or rectangle actually, 10.5 inches by 15.5. I am not concerned with the height, because height is actually a other value. I'm not going to do that design in front of you, a 3D design. I'm just going to do a 2D design of the footprint. I am actually concerned with actually having a footprint over there. Now, so I want to make 10.5-inch line first. So I will go on this one. Now over here, please select top overlay. This is very important. You have selected top overlay over here, and by using this top overlay, now I will select simple track, and I will make actually this goes on to I want to use top overlay. Okay, it's let me just use the red color one, and then I will. So I've just made ambiguously one line. Now this is a line, and I want this line to be 10.5 mm. Now this is very carefully 10.5 mm. So what I will do it, I will first of all double click it. The first thing first, I will make it a keep out layer, or sorry, top overlay. Okay, because I want this one in the yellow color. I can use this one in the red color also, and then at the end I can change it. It's totally up to you. Now you can see very carefully over there, the x dimensions is 68.775. The x here is also, so this is very important that you are actually having exactly a straight line. So this is something, and now I actually want a 10.5. So I will first of all make it something in here. So this is 73, and here I will make it something 83. What was the dimension? Let me just go back to it. This was 10.5. So I will have 10.5. So this will be 83.5, and this will be okay. So what I have done, I am zooming in. I have now a vertical line, and that vertical line is this outer part. This is 10.5, and I will require another 10.5. So what I will do, very easy one, I will select this one, and paste another one. So I have now two. Now I need to draw the horizontal lines. Now the horizontal lines, if I go back on my data sheet tells me that the horizontal physical size is 15.5. So I will go back again, go on this tool, that is the track tool or the line tool, you can call it, and just make an ambiguous line. Again go on this one. This time the y size has to be same, because it's going to be a horizontal line. And here I will make it supposedly 70. I'm just using, I could have used that value and then multiplied it by 15.5, but just for 70 I will make it 85.5. Let me just confirm it. Yes, this is 15.5. So I have now 15.5 length horizontal. I will change it to again, sorry, top overlay. Okay, so what I have done now, this is another horizontal, and I have placed it. Now I need to connect these four. Okay, so what I will do, I will bring this one, I will select it. Now this is very important how you are actually going to move it. Select it first, have Control X, okay, Control X, and click on this point where the ending is there. So when you have selected it, again Control V and bring it close to this point, and similarly and again place it actually I've done a little wrong. You can see the distance, and if you had not done that X and Y, again it's not that good. Anyway, let me just try another one. Okay, yes, this is one. So I have attached three sides, and now I will just zoom in this one. You can see what I'm doing, and technically it should be aligned. So now what I have done, I have a rectangular box of 15.5 cross 10.5. Now I just want to confirm that it is exactly the same dimension. I will again use the ruler, and here I will just zoom in a little, and okay, you can say a little bit decrease over there, but anyway this is approximately 15.5. Let me just, and I want to have this dimension So this is 10.45 or 10 point. Now this is a very small difference, but I won't say that you can't proceed with this one. I will proceed with this one, and let's see at the end how much this is over there. So this is 10.5, this is 15.5, assuming that this one. Now if you can't play with that accuracy, I will advise you to go to again board options and change this value to something 0.1 or 0.25, because when I made it 0.025, this is actually making it difficult for me to actually make that orientation over there. Okay, now you have this rectangular box. Now based on this rectangular box over here, I have, if I go back on my data sheet and if I see again on this data sheet, I have over here two pads first, and they have a distance from their center to center of 7.62. Okay, and that is also shown over here in this diagram. So this is a 7.62 distance, and the distance of this two pins from the edge of the over there is 1.6 mm. So what this means over here is this, that I will require on this one from this side over here, I will have to make a track supposedly and make it 1.6 mm. Okay, so what I have it, I have the starting end as 82.7 and the ending end as this is 81.25. so this is approximately whatever the distance, sorry, on that one, 1.6. so I need something, I need over here 80 1.6. so this is going to be 84 point, so let me, I guess that will be better if I can have a calculator over here. 82.7 plus 1.6, sorry, so this is 1.6 and I have 84.3. so this will be okay. So you can see now, and this is a still slight, you can see over here. So what I will do, I will make it center. So now what this means, that at this line over here, so when I will do it, I will have from this point, I will make a line. This is just a line over here so that I can actually extend this one. I guess there is some issue over there on the okay, so I guess okay, coming back to this one. So I have this I'm just going to extend, okay, it's not extending, so I will just extend it myself over there. Okay, now I have a line now, and on this line I am going to place two pads. So if I go back on my data sheet, distance of 1.6, I have a pad. Now how much distance from here, this is 1.6, how much distance from here, can anyone tell me on this one how much distance it should be from this side over here? So if this is 7.62 from the center, so this means if this is 10.5, let me just have a calculator over here. So this is 10.5 minus 7.62. So this is 2.88. So 2.88 divided by 2. So this is 1.44. I'm again doing it. Listen to this very carefully. This is a 10.5 is the exact length. 7.62 from the center of this pin to the center of this pin. So that distance, if you divide it, that is 2.88. So 2.88 divided by 2. So this point to this point, this is going to be 1.44. And from this point to this point, this is also going to be 1.44. So this means if I go back over here, here I will require a line over here at one. So at this central point, I will have it. And in fact, let me just delete this one for my sake. In fact, it's difficult. Let me just make that link. I will use some other layer so that I can have it. So this is again, and here I am going to make it. Okay, this has changed to top layer. I want to use bottom layer over there. Okay, so this is bottom layer, and I want to select this one. So I want to make it how much length? I want to make it 1.44. So I will again see it. This time the Y dimension is going to be changed. X dimension is same, 82.675. So it is starting from 82.075. So I will add 82.075 plus 1 point, sorry. This is 82.075 plus 1.44. So this is 83.515. So this is going to be 515 and over here. So this means that where this is, and I hope this is having a still a little, okay, like this. So where this is having, at this point I am going to place a pad. So I will select a pad from here and I will place that pad over here at the exact where this is enter at this point. So this is my first pad I have placed over there, which is at a distance from this center. Now let me just confirm it. I will again go on this one, select this one, and I have to keep it as straight as possible, and you can see this is 1.6 mm, and I want to confirm the above one also. So this one, and so this is 1 point, you can see I have taken it 1.44. So I hope you are getting what I am doing over there. Same thing, I will copy this line because I need that line over here, and I will cut this again from this point and place this at the exact center. You can see now while my mouse is hovering over here, and I will place a pad again. I will select this one over here and then take the pad and now place it here. So now what I have now is two pads placed over there. I'm still not going to save this file, I will do it afterward. So this is a two pads placed over here for the relay over here, which are these two pads. The next two are very simple because they are just going to be placed at 2.54 mm. So 2.54 mm is a very small distance, and I can do that very carefully, very easily by just using a ruler. So this is one ruler and I can make it. Now I will just place it over here and again double click it, and this time the Y is 74.5. I will make it again also 74.5. Starting is 80.075. So I will make it 82. You have to always have a calculator actually because you are working in coordinate system. So this is 2.54. So this is 82.615. So 82.615 straight line, and you can see now. So you just have to manage this again because this is going to be, yes, now this is at the exact center, and here again I can now place a pad exactly at this point. So you can see now I have placed two pads, and based on these two pads now I can have another pad placed. Let me just take this one and place it here for the next pad. So this is going to be your fourth pin. So now when you have placed 4 pin over there, now you need to have the last 2 pins which are available over here on this side. Now here still the dimensions over here from this pin to this pin, this is 10.16. So this means easy way around. What I will do now, I will take again this one, I have already have it, and I will again double click it. Starting is 73.024 and the ending is 75. So what I will do it, I will again go on this one. This is 10.16, just confirming it. So I will go on 10.16 plus 73.024 and I have it 83.184. so 83.184. click OK and I have it here, and I will move it. So you can see I placed it here, and this point where it is actually, since this is a straight line, I don't need to confirm anything. I will take a pad. Always whenever you are going to place a pad, please select these arrowheads and then take a pad. This will give you the option so that you can place it exactly at the center. Okay, And similarly I will take this one and place it over here. Always use this one as this one, like this. And then there is a pad. Let me just select first select, take a pad, and then you can place it at a center. So now I can take off this arrowhead, and I can again use a ruler just to confirm, and from this pin to this pin you can see this is 10.16, and from this pin to this pin again 10.16, from this pin to this pin again 2.54. So this means that what I have now successfully made, I have made 6 pins over here, and now I can take these arrowheads away. I can also take this red and blue color lines because I don't need them over there. And this is my relay, which will be actually visible on the footprint model. Now it's still not saved. Okay, I have to take it in the PCB library. So what I will do, I will select this all, click copy, Control C, and maybe click anywhere. Okay, all of this is copied. Go on file. Okay, this is very important. Go on file, click on new, click on library. Okay, you are creating actually a new library, a new footprint. Click on library, go on PCB library. Okay, you have again now a PCB library file. It's still not unsaved. You will click on Control V. Now you have the mouse and you place it. Now it's still not finished. You still have to name those pads and all that stuff. Now it's totally up to you, because in your data sheet they have not given which is pin or which is pin, whatever it is doing. So I will advise it, because you are going to use this model designator, call it Coil A. Okay, click on this one, designator Coil B. This one is normally open, NO. This one is normally closed, NC. And this one is common, which means the common point where you are actually going to have the AC supply. So this is common. And now you're so, and if you want to add some text or strings over there, so because I want to actually add a string, so I will double click this one. This is HLK400F / 5 volt relay. Let me have it dash 5 volt. Click OK. It's actually a little larger name, so what I will do it, you can see now in this one you can only work in mils. In PCB library you can only, I could have drawn this over here, but I would have to work in mils, so it was difficult. That's why I designed it inside a PCB, because there you have the provision of actually using a millimeter. And now here, since you can see the height and all those are in mils, mils is actually a subunit of inch over there. You can text it out yourself also. So I am just decreasing it over here, so that now I can call it in this one. And very importantly, I want it as top overlay, as yellow print over there. The second last thing which I have to do it, click on edit set reference, that is center. Okay, so the pin center, whenever you are going to select this device, so this is the pin center over here. We have called it common, Coil A, Coil B, NO, NO over there. The last thing, you have to give the name to this one. Click on tools, click on component properties. Here you will write down HLK 400F - 5 volt over here, and here you can have the height. Now the height of your device, if you remember it, that was shown over here, that was 11.8 mm. Convert this into mils and you can have it also. At present you can just write it down as something like 50 mils or whatever. I'm not going to do that conversion. You can do it on your Google. Click on OK, and now you have your device. Now you have to save this library. Click on save. Now I want to save it in my LTM library. These are all the libraries which I have made. Some of the many libraries you have used up till now are also made by me. So I will call it HLK 500, actually it was 400F - 5 volts. I hope I'm not superimposing. Yes, I have already. You can see this is HK, sorry, not HLK. This is HK actually. HK 400F - 5 volt, and here I will call it EEW because I am designing it with the electrical and electronics workshop, and click save. Okay, now it is saved. Now I will go back to my PCB file over here. Let me just close it. And since this is a PCB file, and now I want to use that PCB library which I have made. I will click on place, go on component. Again, it will take some time. Now this time I have to add a library. I will click on this one, and I need to install a library. So I will go on in Altium library, and I have saved this one just now. It is here. So this is HK400F-5 volt. Click on open, close, and now you have it. So this is the footprint available. So you have successfully designed the footprint of, you can change the name actually, I have falsely called it HLK, this was actually HK400F. So you can have, and you can call it relay 1 or relay 2 or whatever, and you can use many footprints like this over there. And in fact also you could have also changed the pad size. I not use 2 mm, you can use 2 mm there also, but practically this is the way you are actually going to make a model. So practically I have made in front of you a model of a HK4100F 5 volt datasheet over there, and you will do the very same for the power module. This is actually the same power module datasheet, that is 5 watts ultra small series power module. The one which you are using is HLK-5M05 over there, and based on this 5M05, this is just a 4-pin device, nothing substantial, nothing thing. You can do it very easily. And if I tell you a little properties of this one, this is actually having an output watt of 5, output voltage of 5, output current of 1 ampere or 1000 milliampere, same thing. So there are some things over there. You can go through this data sheet over there, some technical details about the temperature, humidity, and the variations in the voltage over there. What I'm more concerned at present for you is actually the shape of the pin configuration, which is actually written on page number 12 over there. These are dimensions in the weight. So from the bottom side, this is from the bottom side. Please remember, this is the bottom view at present. This is 38 is the outside dimension, 23 is the outside dimension, and then these are 2 pins which are the AC pins. Here you are actually going to connect the AC voltage, and then these 2 pins are 20.5, yes, not 20.5, this is actually different. So this is 20.5 minus 2.5. This is very important, please very carefully. So this is 20.5 minus 2.5. This is the distance between these 2 pins, and from this pin to this pin, this is 35.8 minus 2.2. I hope you can actually see this one. And one thing very, very important, do not design it without seeing the data sheet, because here you have AC input. This is the top view. So positive is at pin number 4 and negative is at pin number 3. So when you are seeing it on a side view, you will see these 2 pins are the AC pins, and this pin are the output voltage pin. So practically, physically, you have all this data sheets and all the pin holes and whatever. So you have to actually design a PCB in which these 2 items are there. The first item is this power module, and second item is this HK4100F. This is actually shown in black color, but I have actually over here at Hall Road you are available. So you have to make the 2 footprints of these 2 devices, and then as far as the running is concerned, you are actually going to use the same MMBT3904 NPN transistor. And in this transistor, the only change over here is this, that this transistor is now connected on the low side. As you can see, the coil over here is connected with 5 volts already. The other end of coil B will be connected to ground when the transistor is turned on. So here again an SMD transistor over here working with an SMD resistance, which is going to be connected with 1 pin of the male header, and then there is a bleeder resistor. Now this bleeder resistor is very important over here. This resistance, supposingly there is a turn off of electricity or something, and maybe your device or smartphone is not working and it's not giving any signal on this male header pin. Certainly there is going to be a microcontroller, and that microcontroller is going to give that signal, so that the transistor, supposedly the transistor was turned on and then it was in floating condition. Floating pin means that it's not 5 volts, it's not 0 volt. So what will happen? The transistor will remain turned on. It will not turn off because the current has not gone to zero. It's not gone to. So this resistor, which is actually a bleeder resistor over here, this will actually make that transistor turn off because this is going to give to the base a 0 volt. But this is a 10K resistor, so it will take some time. So it's not going to be problematic. So it will take some time, but it will turn off. So if your microcontroller fails or your signals to this male header fails, you are going to have a issue over there. So this bleeder resistor just between the base and the emitter over here. And then one thing very important over here, that is parallel to the relay coil, that is coil A and coil B, you are going to use a diode. I hope everyone has an idea what is a diode and anode and cathode device. And here this diode is again going to be an SMD diode. The number is going to be 1N4148W SMD. That is going to have a package. This shape which I've shown you over here is an SOD123. SOD123 packaging of the diode. And what this diode will do, now listen this very carefully. Supposingly your male header pin gave a 5 volt signal to this transistor. The transistor turned on, the relay started to have a current. What happened? The common point was connected to the live. The normally open point was connected to this barrier block connector, and from here there was like devices, wires were going on. Supposedly there were like 8 devices. The first 4 were fans, the next 4 were the bulbs or whatever devices over there. Now you gave a off signal, okay, from the male header. So what happened? The transistor turned off, and it will eventually turn off. But this relay coil, it is an inductor, and I hope you have an idea from your circuit analysis course, which is also going on at present, that an inductor will not allow the current to change instantaneously. An inductor has the capability that it will try to store its energy as in form of current. So this inductor current will not go down to zero over there. So this diode connected in this direction, this is very important, in this direction will allow that current to hover or rotate inside it in this form unless and until it dies down. So this relay coil will be saved from a high spike in voltage. So this diode is a must because the coil has an inductive nature, and that inductive nature is going to make the relay have a fault. So this is very important that you have a 1N4148W SMD with a packaging name of SOD123 parallel, but in this direction. I hope you can see this is the anode, this is the cathode. If you connect it otherwise down, certainly this will be coming in question for you will be soldering it, but when you will connect it upside down, this means that the relay coil is bypassed. So current will actually flow through the diode and then through the transistor. It will not flow through the relay coil. Why? Because the diode has a less resistance as compared to the coil. So current always takes the least resistance path over there. So this diode connected in this anti-parallel direction, you can call it anti-parallel because you are actually allowing the current to flow anti from the normal direction, and this is going to be connected 5 volt. So for each relay, you are going to have 8 of these relays inside your PCB, and 8 of those PCB relays are going to be connected with 8 of these transistors and 8 of these resistance and whatever. And there is going to be a male header 8 pin, and those male header 8 pins are going to be connected to these 8 of these transistors. And the relay, one thing, all of those relays, their common point, listen this very carefully, all of the relays, their common point is going to be connected to AC live. And what is AC live? AC live is the connection over here at this point, which is AC live and AC ground connected with a block connector. One thing very important, if you are connecting this AC live and AC ground from your block connector towards this IC, please make this path over here as thick so that it can actually handle a current, plus this AC live to all of the common points, they should be large. Why? Because this current is going to be large, plus the current from the normally open point to these block connectors. There will be 8 of these relays, so 8 of these block connectors. I have shown 4 pin 2 blocks over there. You can connect them in series over there, and then this is going to be the normally open connected to each one of them. So 8 transistors feeding from a common AC line, क्योंकि आपके पास सप्लाई एक ही है, वापडा की तरफ से जो एक सप्लाई आ रही है वो आपने सबको देनी है. आपने फर्स्ट डिवाइस पे फैन लगाया हुआ है, फैन नंबर 2, फैन नंबर 3, फैन नंबर 4. सो कॉमन ऑफ ईच रिले, which means common of this relay is going to be connected all to AC live. Now how this is going to be done, I'm just going to show you one small value over here. Okay, so see over here, this one is a small PCB I have designed over there. It's actually working in my lab also. You can see these are 4 relays and their common points I have connected together. These 4 relays I have common points connected together, and here I am putting that VAC. So devise some strategy in such a way. These are now ये bottom layer पे लगे हैं, so they're not top layer, but if you will take them in top layer, then this will be something like this. ठीक है, this is my model which I have made it, so it's a little different from what I have designed in front of you. So you have to design your relay, you have to design your power module, and then you have to make this block PCB over there. Now two things which are still missing in this whole circuitry, and one thing which is very important, the ground of DC as shown over here, this symbol and this symbol is completely different from the AC ground. Please do not connect them. I have written them in red color over there that AC ground and circuit ground or DC ground, they are 2 different nets. Don't combine them together, and keep the AC portion and DC portion on PCB separate to avoid problems. Why? Because when you are going to switch on the device, that device is having a 1 ampere or 2 ampere current, and there is going to be some interference with the DC circuit, so it's going to have some electromagnetic interference. Just like आप मोबाइल फोन को किसी इलेक्ट्रोमैग्नेटिक डिवाइस के पास ले जाते हो तो आपकी आवाज़ खड़खड़ होनी शुरू हो जाती है. The same thing, whenever you are going to have a device turned on and turned off, your transistor or any other transistor near that is going to have a suffer. So you have to design a PCB in such a way that your transistor section is far away. Now if you see my design over here, this is not SMD, you can see very easily over there, these are 1 2 3 4 transistors, and these transistors are away from the 4 relays over here. Okay, so I have made that, this is the microcontroller also included over here. So these 4 transistors, their resistors and whatever stuff, they are away from the actual relays over there, because relays, they have the AC part also, the DC part also. But yes, again, your PCB design is going to be 2 layer. So what I have asked you, I have written the instructions also, that it's going to be a 2 layer PCB with power module, this one, that is the high link power module of 5 watts, relays, all 8 of those relays, male header, this one 8 pin, and the barrier connector. All of these devices, they can be on the top layer. This is a restriction on it. Why? Because I don't want the PCB volume to be much large, because these are devices which are going to take a lot amount of power or space over there. So these are all on the top layer. The remaining transistors, because they are SMD, the resistance, the diodes, even the SMD LED or whatever the capacitors over there, they're not going to be that much thick. So they can be on the bottom layer. Okay? I'm not restricting, they can also be on the top layer. Sorry. So if you want to actually have the PCB design with a small form factor, keep these devices which I have told you on the top layer, and the remaining devices, and of course the block connector also on the top layer. I've missed that. So you will only have a PCB design of 8 relays over there, which will be controlling 8 devices on these 8 pins in form of 4 pin 2 block connectors over there. These are called as barrier block connectors, and this 2 footprints you have to make them yourself. Lastly, very importantly, in this circuit diagram, there are 2 things which are still missing. Now I was trying to actually confirm them from Hall Road, that this resistor and this capacitor, what type of capacitor and resistor I'm going to use. Meanwhile, up till I will confirm it, don't use these 2 devices. don't use these two devices. When I will confirm it, you can add them later on. They will be through hole devices. They will not be SMD. They are going to be, I was trying to actually get SMD, but I could not find SMD resistor and SMD capacitor of this rating. So meanwhile, I can't confirm them. Don't use these two devices. They are in parallel, so don't need them. Two things I'm asking you to do it. One is this 100 microfarad SMD electrolytic capacitor and SMD SOD small outline diode 123 packaging. I'm not telling the packaging of these two. You have to find it out yourself. Now you are quite familiar with the LTM software. Kindly try to find out the footprint of SOD 123, that is 1and 4148, and this 100 microfarad electrolytic capacitor. I have given the links in the notepad file also. You can go through there and try to find out that what is this packaging and this packaging. The footprint is available in LTM, or maybe you will have to download from somewhere, or easyeda.com. This is one website from where you can download it, but try to find it out yourself. These are very simple components, very small. This is the capacitor over there, and this one. This capacitor, which is 100 nanofarad, which is going to be just SMD 1206. You already are familiar with that 1206 over there. This is going to be, now the reason over here, I told you in the very start that there is a reason that I am not going to have two capacitors over there. It's because this 100 microfarad capacitor is there for big changes in the voltage. Whenever there is going to be a device turn on, the relay is going to take a lot amount of current. So when the relay is going to take a lot amount of current, so what will happen? That current is either going to be supplied by the power module. If the power module cannot take that current surge, the capacitor is going to give it. So it's a very big capacitor. 100 microfarad is a big value. But the small surges, such as something, a transistor turning on or something like that, or small noise, that is going to be given by this small capacitor over there, which is 100 nanofarad. You can call it a 0.1 microfarad. So they have two different, I don't know how many of you have gone through the circuit analysis course and you have an idea that what is capacitive reactance. Capacitive reactance XC is equal to 1 over 2 pi FC. Now a capacitive reactance of a larger value capacitor is going to be different than a smaller value. We will talk about that one, but let me just confirm before that that you have an idea about capacitive reactance. Then I can tell you. But any of the circuits in your whole 4 years, you are always going to see on the power supply, you always will have two capacitors, one very big and the other one very small, so that this will take the large disturbances, this will take the small disturbances in the voltage over there. So in this whole circuit diagram, as you can see over there, you have to find out the device's footprint of SOD 123 and the footprint of the capacitor, that is 100 microfarad SMD silver electrolytic capacitor. You have to do it yourself. I've written it over there. Search for SOD 123 and aluminum silver capacitor footprint library yourself. If you can't do that, maybe at some time, maybe like 2-3 days, I will tell you on that one also in the WhatsApp group or on the website. But meanwhile, try to find these two and you can make this PCB yourself. The one block connector, this barrier block connector, I've actually been trying to call some people at Hall Road and get this barrier block connector, but I could not find it. So hopefully I will give the barrier block connector PCB footprint a little later on, maybe 1 or 2 days from now on, because I needed to confirm some sizes. I do not have it at present with me. This is called as a barrier block connector for a very important reason. You can see from one pin to the other pin, there is a barrier in between, the black color. So the wires don't connect with each other. That's why it is called as a barrier block connector. This is a 4-pin available also, 2-pin available also. I'm not confirmed with the 8-pin, but yes, 4-pin is easily available. So this is the circuit diagram over here, and these are the instructions written over there. And you have to make the footprint just like I have made just now in LTM for the relay and the high link over here. That is actually the power module over there. Gee, any questions from the class over here? As far as the soldering is concerned, I'm trying to actually get some good zoom in camera or something like that, so that I can actually have another session for so any questions, Ji? Please write down in the conversation window, or I guess the students have been asking, Sir Bilal and Sir Bilal have been asking over there. Any questions, please feel free to ask over here in the conversation window over there. And as far as the announcement is concerned, I have told you also, I am again repeating it. Those who are giving me experiment number 2 and 3 in MS chat, please, this will be the last review I will be taking on. Failure to do that or pass that means that your design is not approved and your soldering marks will be gone, because this is almost now very rare. And as far as experiment number 4 is concerned, experiment number 4, please order your PCBs so that it's available at least in the next week mid, so that and those who have been told with some reviews in your experiment number 4, kindly correct them and upload it with REV1 tag on the same link which Sir Bilal has given you, so that those experiment number 4 changes can be done. And remember that change in experiment number 4 is only going to be done one time. Okay, after that there is going to be deduction, so please kindly do all the suggested changes in experiment number 4 so that you can actually make that PCB and then go towards its running. And please, those who have got their PCBs, kindly start soldering, do it soldering, take pictures from the back side, from the front side, and upload it on the link given by Sir Bilal. And please take those pictures in well illuminated space without flash. This is very important, because when you will have a flash working over there, maybe from the solder points, the flash will be reflected, so it will not be, it will be having a glare over there. So please, with flash off on your mobile cameras or your any cameras whichever you are using over there, so do this one. And for experiment number 4 review, again the deadline is Friday. Okay, so please kindly upload over there for experiment number 4 and all. And meanwhile I will also upload experiment number 5 reviews also by the end of this week. And hopefully when I get my PCB, because my PCB is late for the SMD soldering, I will have another session maybe on Monday, or maybe with the next class on next week we will have it. And this assignment which I have just given you as experiment number 8 is going to be again having the deadline of next Wednesday 12 p.m. just like this experiment number 7 that expired today 3 hours before. So this is your experiment number 8, which is just a simple power module. And for those who may be wanting a simple what should be the dimensions of your PCB, I'm just in search of some ruler over here in my lab so I can actually give you. But normally what I am actually saying it, your total PCB should not be more having PCB visible. It should only have 8 relays, the power module, and those 8 pin block connectors, and that's certainly that PCB block connector, the green color one, whatever you're using, so that everything that is apart from that is available. Because size is very critical over there. If it is size is larger than our switchboard, it can't go inside. So this is very important, that your size should be as small as possible. And whoever is going to design this smallest PCB over here, in this case, most probably I can buy that design from you if you are going to give me a very better design on this one. Yes, certainly the main thing is this power module and this relay, but sadly we have only this choice. If I go to some very better relays, then they are very expensive. This is the smallest relay available. You can see the sizes, they are very small, and you can use this very carefully at for 3 ampere devices. That's not a big issue whenever you are having it. So okay, there are some questions. Yes, you have to use the barrier block connector, and the PCB footprint of this I will share with you maybe by tomorrow or day after tomorrow. Okay. Beta, bakelite and fiberglass in terms of soldering. Bakelite, if you will put the solder iron for a very long time on bakelite, the pad will be eroded off. Fiberglass is a little thick, as the name suggests. It has a fiber inside it, it has a glass like structure, So it's a little robust, it's a little thick over there, and it can withstand heat. Bakelite can't withstand that heat, and as amateurs, maybe you can get your first PCB as in fiberglass, and maybe later on you can go towards bakelite. But yes, if cost is an issue, you should go for bakelite, because bakelite is very cheap as compared to fiberglass. There is approximately a 1.5 to 2 times difference. But we are using a varistor and capacitor because varistor is actually a device. Let me go a little bit deep into that physics. Varistor is actually a device which is actually going to control the surges, because normally in Pakistan the voltage spikes, if it is a 230 volt system, normally sometimes in summer season, rarely, but in winter season the voltage goes on beyond 250 or even 300 volt. So what will happen? The power module will be burned down. So this varistor will actually burn down itself, because it is in parallel, and allow the current to flow through it and control that surge. But that surge can only be for just like 1 or 2 seconds, not more than that. So that varistor is actually just like a protective device for that power module. And the capacitor is there so that any small changes inside the voltage line, they are not there. So these are just the power quality items over there. I'm trying to actually get the idea from Hall Road that what will be the size and shape of these ones. So as soon as I get them, I will share with you. And meanwhile, don't need to add them in your PCB design, because as a good design engineer, you should have your device protected from surges and from spikes. Okay, this is very important. Yes, beta, we have to use 2 barriers and 1 simple block connector. Yes, beta. What will be connected to the normally? Nothing, beta. Normally closed pin is connected with nothing. Okay, because we are designing a PCB so that when you want to turn on a device, you will have to give a signal to the transistor to turn it on. I'm not asking for a fuse over there, because then I would have to actually ask you to design another library, because there are some fuses available, but fuse you will have to actually have another library. Yes, you are right, row 136, that we should use a fuse for it. Fuse are very good items, but yes. Yes, beta, both common in the relay. Actually, it's not replay. Both common in the relay will be given AC live. Yes, beta, both common. They both are internally connected, even if you give to 1 pin, but it will be better if you give to 2 pins, because this is AC current traveling through the relay. Remember, this is a 1 ampere or 2 ampere or 3 ampere current flowing through the relay. So this point, AC live, connected with this common point over here, this point has to be thick, and from normally open contact from this pin where my mouse or cursor is at present towards the block connector, this has to be thick. And when I'm talking about thick, at least 1 mm, maybe like 0.8 to 1 mm, at least 0.8 to 1 mm. This is the minimum thickness for this one, because there is going to be 1 ampere current. And one thing very important, this PCB can't be made on bakelite, because 1 ampere current, if it is flowing through this PCB, it will be heated out. So bakelite is never the solution. Maybe then fiberglass with some good thickness of the PCB has to be there, or the copper over there. If you want to make SOD 123, yes, you can do it, but SOD libraries are available, so don't need to go into that. Just make 2 libraries of whatever. They are internally short circuited, but I will advise you to have both pins connected to live AC live, because that will share the current then. So the stress on 1 pin is going to be small. You can see this is just a simple small pin. So 1 pin handling that much current, it's going to be difficult. So it's better if you have both all pins over there connected with the AC live over there. This is a very good experiment. It's actually, I'm doing this kind of an experiment for the first time. Last time we also had some relay PCB design, but this one is a little different, because here I am asking for a power module from the AC voltage line, and then we have the barrier block connector also for the connections. And one thing very important, the 8-pin male header, that is for the control over here, and the 8-pin barrier connector, they should be preferably at the edge of the PCB. This is very important. Just like this PCB which I've shown you, you can see my block. This is actually block connectors. I have used it. I have not used those barrier block connectors. That's why I don't have the footprint with me. So you can see this one, and this one. They are at the edge of the PCB. They are at the edge of the PCB. So you can see I can access them. Otherwise, if they were in the middle of the PCB, it would be difficult. I am using over here this block connector for 5 volt and ground. There is no the power module over there. I have another version of this PCB in which there is a power module also installed over there. So please have these items over there in on the edge of the PCB, so they are actually accessible whenever you are actually going to put that, because any one module, whoever is going to design the very best module, and the next soldering video when I will make it, hopefully that will be for roll number 16. Thieves, I guess, is the again winner over here for SMD PCB for yellow dot matrix, and hopefully when that PCB arrives with me, I will do that soldering again on camera, and that's going to be again, I'm not going to ask you to do the SMD soldering. We will wait for the SMD soldering, hopefully. I'm not confirmed. Hopefully when university will open. Before that, we will complete this experiment number 2, 3, 4, 5, and some portion, whatever we have it. So those people, I have been getting some messages or emails lately from last 2-3 days that they're not getting their PCBs up till now. Don't worry on that one. Actually, it's Ramzan time. I had a word with Mr. Al-Jalil also. Sorry, Mr. Mukarram, who is actually the owner of Al-Jalil PCB. He also told me that he's also having some problem because of the timings. Because at 6 o'clock they have to finish it off, and then there is Ramzan over there. And then I had a word with EPCB. They were also having the view that your files which are submitted, they are having so many problems that the editing has to be done. And what were the main problems? I have told you previously also that to make your text at least of 1.7 mm to 2 mm height with a thickness of 0.3 mm, because if you make it very thin, it won't be printed even over there, because if they are using UV light for that PCB, or even if they are using some other method for it, if it is very thin, it won't be actually be visible. So your PCB will not be having those names, so your name will not be there. So please have that. So I have asked them personally that to make that editing over there. So they are taking time for that editing also. And secondly, they have other problems of haphazard tracks over there, because I have approved them, but yes, there are some problems still over there in your PCBs, such like haphazard tracks, that there is a straight line and then there is a little fuzzy line again going on, and then so whenever you are making a PCB and such like thing happens, and then that PCB goes inside the acid, the ferric chloride solution, it will be actually eroded off from that haphazard point. So this is very important. So they have to edit your PCB, and then when we will order that SMD PCBs and all those vias, then I will tell you that what should be the hole size. And that point, it will be very difficult to actually ask the manufacturer to actually make the via holes of just 0.6 mm and then the other holes over there. And I have asked, and there have been some cases actually where they have been missed some holes over there. So I have told this cases to EPCB.pk also and Al-Jalil also. I don't know Al-Jalil has done this mistakes or not, but yes, this happens whenever you have a manufacturer here, and when you are only just having one PCB, then certainly, because when you have like 10 or 12 different PCBs, they actually stack all the PCBs together, and then they use one drill machine to drill the hole from all of them simultaneously. So this is very important. So when you have only one piece, then they don't actually care also for that one. So this is very important. Anyway, any questions, G? So please kindly do this one, and I will share also experiment number 5 review sheet with you at the end of this week, hopefully. And this is experiment number 8. The picture is there, and I have to confirm on 2 things over here. The first thing is the barrier block connector footprint, which I will share with you, and the second thing is this resistor and the capacitor sizes. There will be through hole, there will be certainly be through hole. I confirmed from Hall Road that they are not available in SMD, but if they are through hole, then what size and what dimensions I will tell on that one. And meanwhile, try to find out this electrolytic silver capacitor, which is actually aluminum silver capacitor, and then the small outline diode SOD 123. They are different diode packaging, but this one 1N4148 This is going to be SOD 1, 2, 3 over here. Yes, beta has a step. No, it's not having a step down transformer. It's not has a step down. If I had used a step down transformer, उस PCB का size ही इतना बड़ा होता कि वो इस PCB के बड़ा हो जाता. So it is an isolated AC to DC converter which is employing some very high power, high frequency power electronics. You will understand this when you will reach your final year or maybe like sixth semester when you will be having power electronics course in detail. Okay? So meanwhile, keep your questions, whatever you are going to. In fact, many of these questions will be answered when in the next semester we will be having a course of analog electronics or maybe circuit analysis and design or such like. So it is not just rectifier, it's a rectifier with a DC to DC converter with an isolated approach. One thing very important I have told previously also, and one again, that the AC ground and the circuit ground, they are two different things. Kindly don't make them common. If you make it, it is going to be catastrophic and the whole PCB is going to be burned down instantly. Okay, so this is all, and for experiment number 8, any other questions?